Next, we are going for integration of second order parabolic equation. So it is given by y is equal to ax square. So I can write this as y is equal to ax square. If a is equal to 1, I can write this one as y is equal to x square. And as usual, we are having our Riemann rectangle strips, and we have our slopes here. So this is delta y, and this is delta x. So now we can write that delta y is proportional to dy by dx. So we will start with y is equal to ax square, or I can write y is equal to x square. So dy by dx, I can write it as 2x. So we can find out the dy by dx at different points to validate this. So dy by dx, I can write this as at x is equal to 1. So it will be 2 into 1, this is 2. And then we will try to substantiate by delta y by delta x at the same point at x is equal to 1, which we have gone from the top of the Riemann integration strips. Okay, so at x is equal to 1, so we are finding that this is approximately 1 division, and this is approximately half the division. So I can write this as approximately 1 divided by 0.5, so which is approximately equal to 2. Okay. So next we can validate in one more point, so maybe at 2. So dy by dx, we can write it as x is equal to 2. So this will be 2 into 2, this will be 4. And now this I can write it as delta y by delta x. So this I can write it as delta y. So delta y is up to 2. So up to 2 delta y. It is approximately equal to 2 or around 3 divisions, and this is around 0.75. Again, you will find that it is approximately equal to 4. Okay, so that is how we are having that our delta y is proportional to dy by dx. So that is what we are finding here. And again, we are finding that the variation of the slope, it is linear. So here you can see that theoretically what we are getting is variation of the slope is linear. And here also, visually also, you can see that the variation of the slope is linear. That is what we have substantiated here also. Next, we can go for one more type of curve in the same category. So that is y is equal to x square by 2, which usually we take it for the integration. And so for this, we can find out the slope. So this dy by dx is equal to 2x by 2. So this will cancel, it will be just x. So it is easy for checking. So here also you can validate for 2 or 3 places. So I have dy by dx. So I can have that x is equal to 1. So when I put x is equal to 1, theoretically this value is 1. I put a delta y by delta x. So I'm sorry, it is delta y by delta y by delta x is, it should be approximately equal to 1. So here you can find that it is almost delta y is equal to delta x. So this is validated. And similarly, we can do it at 2 also, dy by dx at x is equal to 2. So when I put 2 here, it will be just 2 only. I put delta y by delta x. So this should be approximately equal to up to 2. So here you can see that we are having 2 division approximately, and 1 division approximately. So again 2 by 1. So again this is 2, and this validated. So here we can even wait for delta y by delta x for the x is equal to 3 also. So here we are having 3 divisions by 1 division. So just it is 3 by 1. This is approximate. Okay. So all these discussions substantiates that the variation of this slope, okay, it is linear. That is what we finalize from this discussion. So we can conclude that delta y for this layer is proportional to slope dy by dx, okay, which is proportional to maybe kx or ax, whatever the case may be. Okay, so it is in the linear form. Okay. It is in the linear form. So whether it is ax or kx, so it is in the linear form. Next, we are going for the integration of third order cubic function. So third order cubic function it is shown here. It is y is equal to ax cube. And these are all the usual Riemann integration strips. And we are trying to find out what will be the slope. So this is delta y, this is delta x, this is delta x. So if I have the function y is equal to ax cube, so the differentiation of this will be dy by dx will be 3 ax square, which is nx power n minus 1. And you can consider that a is equal to 1. So this you can take it as 3x square. And this function also can be validated at delta y and delta x. So we can validate at 1 and 2. So first we find out the dy by dx at x is equal to 1. And that is 3 into 1 square. This is 3. Similarly, we can validate at dy by dx at x is equal to 2. So this is the exact solution. This will be 3 into 2 square. And this will be 12. 3 into 4, 12. And this can be validated by the slopes in the Riemann integration strips. So I write this as delta y, and this is delta x. So this I can find out at 1. So when I find out at 1, this I will have it as delta y by delta x. So that is 1.4 by 0.7, or 1.5 by 0.5, 1.5 by 0.5. This is approximate. So this is approximate. So I am getting approximately equal to 3. Similarly, here also I can find out that is at x is equal to 2. Also I can find out what is delta y by delta x. So this is approximately equal to. So here you can see that there are 6 divisions. 6 divided by 0.5. This exact 6 divisions divided by 0.5 division. So this is I have 12. So here also I have 12. Here also I have 12. Thus it is validated. And the most important thing what we have to note here is the variation of the slope function. Okay, so the slope function is quadratic of the square curve, and the variation is given. Okay, so you can find that is the variation of the curve. Okay, so the variation of the curve is the square curve or quadratic. Okay, so that is what we have to conclude from this discussion. So when I differentiate the third order cubic function, so I'm getting the second order square curve. So the variation of the slope also it represents the same thing. So that is what we conclude from this discussion. Thank you.